All right. Well, welcome. Good morning to another coding lecture. Thank you for dealing with the number of coding lectures in a row. I feel like we got to handle a lot of examples so that way people can do the homeworks when they come out and have a lot of good references for that. So today I want to cover quadratic programming, some quadratic programming examples, a few course updates, quick course updates. One, I still want to re-record the very end of the constrained minimization lecture. Don't fret, I won't ask you to do anything on that lecture until that's all finished and recorded with good coding examples for you. That's number one. Number two, expect your homework number 2 to come out, and that'll be fully focused on optimization. That should come out hopefully in the next day or so. I try to give about 2 weeks to give these assignments, and as you probably have learned, it's a good idea to start on these things a little early, not because they necessarily, if you know exactly what you're doing from start to end, it might not take that long. But figuring out what's going wrong with your code, as many of you probably learned, takes some time, right? And so please get started on homework 2 as soon as that comes out if you could. And number 3, projects. So we're actually hitting the point where you have enough background information on how to simulate mechanical systems, simulate systems of all kinds, that you can actually start drafting up some project ideas. So I'm going to be releasing information about the project and what those due dates are going to be. But the first stage of which is going to be a proposal. Okay, that we're going to want to have people submit a proposal of what they want to do. Sometime the next 2 weeks, I'll send out the announcement. If you are a graduate student, this will be an individual project, unless you have a particular project that's going to require more people, at which point I want you to talk to me about it. If you're an undergrad, I expect you to work in groups of 2. If you want to work in a group of 1 or a group of more than 1 and you're an undergrad, let me know. Okay, that way you can talk with me to make sure the project is appropriate. But you want to write a 1-page proposal as to what you want to do for your project, and it's going to be a project again that you simulate and you control with some kind of optimal control method. And this will be in place of your final exam. All right, there won't be a final exam, but what there will be is this project that you work on throughout the course. At the end, there's going to be a PDF report that you're going to submit. It's going to be actually in the format of a scientific conference paper or scientific journal paper. I have a format all laid out for you to follow. And it'll also require for your group a video. Okay, a 5-minute video of you presenting your work as if it was a PowerPoint, and you submit the video as part of your final presentation. There'll be a few checkpoints throughout the semester. There will be the proposal phase. There will be the draft phase, where you have to show that you can simulate your system even without a controller. There's going to be a controller draft phase where you're going to show some kind of control, preliminary control of this system that you choose. And then there's going to be the final report and presentation. Okay, so I'll try to evenly space those throughout the term. That way you're getting check-ins on how your project's doing. All right. So that'll be the project. One non-ideal thing is I would love to have, whenever everyone's in the room, an opportunity to pair up if you are an undergrad and you're looking to pair up. Now, you are more than welcome to start pairing up if you know someone from the class, to reach out, say, hey, what do you think of this project idea, and come up with your groups of 2. But what we'll do on Tuesday, when we are back in person, is we'll have everyone get up at the beginning of the lecture, and hey, everyone walks around, says hi, and if you need a partner, that's a great opportunity to meet a partner in real life. Okay. All right. So that's the information on the project, the upcoming homework, and that's it for the moment. Any questions about the course so far? All right, I'll give it a 3 count. A 3 and a 2 and a 1. All right. So we are going to continue now with our lecture from last time. Last time, we were covering the subject of linear programming. So here we are on the 13th. And last time we did some linear programming. Where basically we would set up LPs or linear programs and we would solve them. That was last time. Now today, and let's recall what a linear program was. Let's write down what a linear program was. So we write it out in saying that you have some decision vector, W, and that star represents the minimum or the optimal, okay? It's equal to the argmin, where you're looking for the set of decisions W that minimizes some function f of W that's linear, okay? And the way we write that is C transpose W, okay? Because C contains all these constant coefficients. We showed all kinds of cool ways that we can calculate that C. And that C is also known as we know, the Schmadiant. Sorry, the gradient. The gradient. It rhymes with Schmadiant. The gradient. Okay? All right. Subject to the constraints, you have linear constraints. AW is less than or equal to B, and AEQ W is equal to BEQ. If we can put an optimization problem, or a program, as we know it's called, in that form, then it's a linear program. And linear programs are convex, meaning that the local solution is as good as the global solution, which is fantastic. If you want to learn why, the book Convex Optimization by Boyd is part of your reference material. Boyd and Vandenberg. It's a wonderful book on convex optimization and some convex analysis. I actually just bought it in hardcover because they put it online for a long time, but I bought it in hardcover. It's so interesting and important and very easy and relatively easy to read, I would say. But that's in your reference material if you want to learn about convex optimization in general, or Boyd and Vandenberg, okay, convex optimization, part of your reading material. I didn't want to misspell Vandenberg. I forget where the H's are. Okay. All right. So linear programs are convex. But we also have, today we're going to cover quadratic programs. Or QPs. Okay? And recall the way we wrote that is it's, again, an optimization problem where W star, or W asterisk here, is equal to the argmin, meaning we're looking for the W argmin. We're looking for the W that minimizes the function 1/2 W transpose H times W plus C transpose W. Where this here, these are your linear terms, same as your linear program, and this here are your quadratic terms. Okay? And we know that this here is our gradient. And this H, instead of being our gradient first derivative, it is our second derivative, which in general is called the Hessian. Okay? So it has a quadratic program has this quadratic cost. It becomes quadratic because you're multiplying your decision variables here by your decision variables here, so they become quadratic terms, okay? And subject still to linear constraints. Again, not quadratic constraints, linear constraints, and they look just like the same ones for the linear program. AQ W is equal to B. Okay, same ones. So you still have linear constraints, but you have a quadratic cost function. All right. So that's what a quadratic program is, which means that if you have a quadratic cost and linear constraints, you can fit it in that form. Now, are QPs or quadratic programs convex? Well, let's reason through it just with a simple example. Are they convex? Well, they can be. I can think of one example where I have just one decision variable, W. I'll call it W or X or something. We have W. And you have some cost function, f of w, that's a parabola that looks like that. Okay? I know that the minimum is right there. And that's the global minimum because it's a parabola. There's no other extra kinks and going on in the parabola. You know there's one minimum of a parabola. Just by mathematically, you take the derivative, it's only going to intersect 0 at one point. Okay? So this is, yes, that is convex. However, what if it's shaped like that parabola? Okay? Now, all of a sudden, there are two different directions that you could go to find some local minima, right? Left and right, okay? They both, in this case, they both go down to minus infinity. So you might say, yeah, minus infinity one way, minus infinity the other way. They're both equally good, so it's convex. No, not actually, though. Because once you put constraints on this, let's just say you had a constraint that said you can't go past here, then all of a sudden you have two minima. One over there and then one down there. Okay? So when it's concave down, it's not convex. Okay? So not all quadratic programs are convex. Okay? Not all QPs are convex. Okay. But you can sort of see from this example some examples of where it would be convex. As we kind of mentioned this before, that if it's concave up, then it's convex. If it's concave down, it's not. Okay? Or more specifically, if it's concave down, it's not. If it's concave up, yes, or if it's flat, it's yes. So you would say they are convex if the cost is not concave down. Okay? Which means that your Hessian H is greater than or equal to 0. Okay? And if your Hessian's just one number, because you only have one decision variable, that's a really easy thing to check. You take your second derivative, see if it's greater than or equal to 0. Okay? But your Hessian, as we know, the Hessian is a matrix when you have multiple variables, right? It's going to be partial squared f partial x1 squared partial squared f partial x1 x2, assuming that your decision variables are x1, x2, etc. We have this pattern written out where it's partial squared f partial xn, etc., until you get to partial xn squared out to partial squared f partial. I apologize. It's partial n partial x1. I'm sorry, partial xn squared. So you have a matrix there. All right. And what this means, this condition still applies, but this greater than or equal to, when you're talking about a matrix, it's what we call positive semi-definite. Okay? Positive semi-definite. And what that means is all eigenvalues of H are greater than or equal to 0. Okay? I'm not going to go much into a review of eigenvalues here. We got too much to cover. We can just show you in practice for those people who haven't seen it before, but you can compute them in MATLAB, your eigenvalues. There's a really fast way to do it. Okay? So let's take this exact example, this kind of example that I showed you, right? And I'm going to put it into MATLAB to try to solve, okay? This little cartoon that I drew out, all right? So I'm going to scroll back up to, well, I don't know. I'll just redraw the problem down here so you can keep drawing here. So let's have an example. Let's say that W has just one decision we'll call X, all right? And our cost function, f of W, is equal to x minus 1 squared. And let's say we have a constraint that x must be greater than or equal to 0. We want to write as a QP okay? Which means we're going to need three things. We're going to need C, which is our gradient, H, which is our Hessian, and we're going to need all of our constraint functions, which are going to be A, B, AEQ, and BEQ. So one thing we can look at is that we only have inequality constraints. So that means that we don't have AEQ and BEQ. We can just pretend they don't exist here. Let's cross them out. And if MATLAB ever asks for them as part of your quadratic programming solver, you just give it an open close bracket, an empty vector, and it knows what to do with that. Okay? All right, we will have A and B because we do have an inequality constraint. We will have C, which is our gradient, and H, which is our Hessian. Okay? All right, so C is going to be equal to the partial of f of W partial W. That's our gradient. And we're going to transpose it so it's a row vector. Okay? So it becomes a column vector. We're going to transpose it back into column. Yeah, anyway. Doesn't matter because it could be one by one. But so it's going to be 2. I'm going to distribute that. That's going to be partial x of x squared, of x minus 1 squared. Okay? Which means it's going to be partial x. We're going to do a first hour and a last, so it becomes x squared minus 2x plus 1. Now you take that derivative, and it's going to be 2x minus 2. Okay? All right, that's the gradient And we're going to need the, and one thing you'll notice here is this gradient is not full of constants. And why is that? Why is that? It's because this term that has not a constant in here, this is going to be taken up by the Hessian. Okay, so what we're going to want to do to get our gradient is we're going to substitute in 0 once we have our gradient, so that way it only leaves this little -2. Okay? Now we want our Hessian. Our Hessian is going to be our second derivative. So it's going to be partial squared partial x of f of w, which is going to be equal to partial x of our gradient, which was 2x minus 2. And that's just equal to 2. Okay? So friends, is that going to be convex? The answer is yes, because greater than or equal to 0, so it's convex. Okay? We want to substitute in 0 up here. That's going to give you gradient of -2. Okay, so that should be our cost. That means if our cost function, f of w, is equal to 1/2 w transpose hw plus c transpose w, that means it's going to be 1/2 x, because x is our decision variable here, times 2 times x plus -2 times x. That means it's going to be x squared minus 2x. That's our f of w. Now, is that equal to our original x minus 1 squared, which is equal to x squared minus 2x plus 1? Almost. It's just missing that constant, right? Now, is that a problem for this optimization problem that we're missing that constant with our quadratic formula, for our quadratic programming formulation? Is that a problem? Is that going to change our solution? Well, the answer is no. It's not. Okay? Because the function x squared minus 2x has the same minimum value of x as x squared minus 2x plus 1. Why? Well, here on the left, here's x, here's f of w, which is x. It's here's, let's see, x squared plus minus 2x is this, and this function over here is that exact same curve. I'll draw it with a different color. The exact same curve, just shifted up. So the minimum is still here, right? So it still has the same minimum value of our decision variable. So that constant doesn't matter. So it doesn't change W star, which is what we want to know. It doesn't change W star. Okay? So there we did it. We did it. So we have a quadratic program, at least the cost of the quadratic program. All right? For the constraints, we'll whip through those real quick. If we want to have, what is it? X is greater than or equal to 0. We have to put this in the form of some function of W is less than or equal to 0, which means we want to flip this sign, which means we multiply both sides by -1. So it becomes minus x is less than or equal to 0. Okay? If we want the A matrix, we say we want the Jacobian. of that, which so it was a single variable, so it's going to be just -1. That's the derivative of x with respect to x. I'll write that out for you so you don't have to remember. So it's going to be the partial of g of w with respect to w. Our only decision variable w is x. That's our only inequality constraint. Therefore, partial this, partial x is just -1. And on the right-hand side, it's really easy. B is equal to 0. Okay? Therefore, C is equal to -2. H is equal to 2. A is equal to -1. B is equal to 0. And with that, we can use a quadratic programming solver in MATLAB. It's called Quadprog. Okay. So let's go to our MATLAB. We have MATLAB open right here. Okay. I have MATLAB open. Make sure everything works. 1 + 1. Still got it. Still got it. All right. So how do we use Quadprog? Well, we'll say help Quadprog. Help Quadprog. What does it need? What does it need? What does it need? Let's go back here. Here we go. What do you give it? You give it H, which is your Hessian. Hey, look, 1/2. Here we go. 1/2, what it calls X transpose times the Hessian times X. Okay? F, which is what we call C, is our gradient, right? Same thing. Look, this is our exact, look. Look, it's our exact cost function. Look at that. Just slightly different letters. Okay? And you can give it your A matrix and B vector, or if you want to give it equality constraints, you can give it these. You could also give it lower bounds and upper bounds. We did that at the end of last lecture. Okay? There are lots of different options you can use to try to solve it, but we're going to use the basic options here. All right? We don't have an AEQ and BEQ, so we'll just do this. Okay? So let's actually type this out. So we're going to have C is equal to, we'll call it -2. What's H is equal to +2. A is equal to -1. B is equal to 0. Okay. Now we can run Quadprog. We'll say, hey, we want our W star, our optimal decision vector, is equal to Quadprog. You want to give it your Hessian, H, your gradient, C, your inequality matrix, A, your inequality vector for constraints, B. And you run it. All right, and it says, you can't quite see everything here. It says, minimum found that satisfies the constraints. How nice, right? And it says that W star is equal to 1. Well, guess what? That's right. Okay, if you actually plot our cost function, okay? Hey, let's actually plot it. Let's just do a little MATLAB practice, okay? Let's create a vector of possible decision variables W, okay? We only have one decision variable, so we'll just make a line of them. So we'll do a linspace. We'll do it from -5 to 5 with 1,000 points in between. Oh my goodness, what did I do? Okay, semicolon, right? And I'll try to be mindful of the screen here. All right, so we have W, and we have our cost function, which is 1/2 W transpose HW plus C transpose W. So let's make our cost F is equal to 1/2 times W transpose, which is, again, it's going to be a 1 by 1, so it doesn't matter here, but it's going to be, excuse me, W transpose. is the apostrophe is a transpose in MATLAB, as we know, times H, which is our Hessian, times W, plus C transpose times W. Okay, I'm gonna run that. Oh, what did I just do? Okay, excuse me. I made a huge mistake. Okay, Control C. Control C. In this particular case, we're going to do, because I want to evaluate this cost function for every single element so I can plot it. I'm going to do a dot multiply. Oh no, I hit enter by mistake. Oh God, sorry. I'm going to put dot multiplies here because I don't want to do a giant matrix multiplication here. I just want to compute a whole bunch of different costs, right? Okay. Now I'm going to hit semicolon. Okay. Now the size of F should just be a 1 by 1,000, right? What's 1,000 by 1,000? Okay. C transpose. I think I'm being too fancy here. I just want to plot this here. The plot looks scary. Well, we don't want it to look scary. No, chill out. Let's not plot this just yet. Okay, Logan. All right, just brace yourself. Okay, we're trying to make this easier. I'm just trying to do W squared. I'm just really quickly off the cuff. So I'm just going to make this W dot squared times H plus C transpose times W, the size of F. There we go. That's what I'm talking about. All right. Look at that function right there. This is just the square. It only got weird because we're giving it a vector of possible points we want to evaluate. That's why. All right. That's why everything's happening. So fear not, friends. So now we can actually plot W versus F. Okay. We plot W versus F. Eventually show up here. Here we go. Less scary, right? This is just a parabola. Just a parabola. And you can actually look at the bottom of the parabola. You can see that parabola is at the decision vector here where it equals 1, right? Okay. But our constraint here is saying that we can't have W be less than 0. So we actually have a constraint line right here that we added. So it can't go to the left of that. Hopefully you can see that. That's this thing right here. If we had a constraint line, we say that it can't be to the left of 0. We could actually move that further to the right over here by changing this expression here. Let's say we want it to be greater than or equal to 2, which means that it would be less than or equal to minus 2 after we have just multiplied both sides by -1. Okay? So we change the B matrix to -2. Say B is equal to -2. And then we do our W star is equal to quad prog. We just reran the same thing, but we now have a different B. Hey, the minimum is W star equals 2. Okay? Which makes sense if you look at that parabola. That if you can't be less than or equal to 2, then it's going to then the smallest you can get is there, if you can see that. Okay. So we could actually plot that line here. We could say, hey, we want to hold on to that plot, and I want to plot that line. I'm going to say that the x coordinates are going to be 2 and 2. And I'm just going to start with some low points and some high points to draw a vertical line. So I want it to go from maybe -10 to 10. I'm going to have a little red line with line width 2 to make it a little heavier. Okay. All right. You can see that line there I just put on the plot. And you can't, that I put on the plot. So it makes sense that, hey, my minimum that I can do is to go boop right there, right? Now, I just changed the B, so I changed the constraints. What if I change the cost function? Let's just say I change the cost function so H, instead of being +2, it's equal to -2. All right? Now, we know that's going to cause trouble mathematically. This should make it non-convex. So what's going to happen in MATLAB? Well, let's find out. let's say W star. Now that W is equal to the H is equal to -2, our Hessian is concave down. Let's rerun it. Look what it tells us. The problem is non-convex. Okay? This W star of 9, I don't think it means anything. Okay? It just stopped. Okay? It's only good for solving these convex problems, but it tells you, hey, the problem is non-convex. Sorry, I don't know if you can hear I have a wild thunderstorm coming in here. So be safe. We're inside for your safety today. Okay? All right. And it might be trivial to check that this is a positive, that this here is a positive, sorry, a non-convex Hessian. It's all pointed down, that concave down. But when you have a matrix, it becomes less obvious. All right. So I'm going to give you another cost function. Okay. So friends, I'm going to make a new cost function. It's going to be a function of two variables now. Okay. So I'm going to define two variables, x1 and x2. Okay. So I'm going to make a linspace from maybe -1 to 1 with points with 100 points. And then x2 is equal to the linspace -1 to 1 with 100 points. So these are my two decision variables. I want to make a two decision variable cost function. And my cost function, I'm going to call it func. And what it does is it takes in I'm going to say at x1, x2. So this is basically defining a function all in one line that takes in x1 and x2. And I want the function to be x1 dot squared plus x2 dot squared. And that should create a function. Okay. Now I want to plot a surface that has all of my x1s, all of my x2s going off into different directions, and a surface of all of them. So what I'm going to do is I'm going to use the command mesh grid to make a whole bunch of points that I'm going to plug into my function. So I'm going to say, if you look at help mesh grid, we covered it a little bit before. Mesh grid, help mesh grid. Okay. Mesh grid xy, you get a vector of points x and a vector of points y, and out pops matrices of points x and y. Again, here's an example. I showed it in previous class, so maybe I shouldn't waste the time. This is all for demonstration purposes. So we'll say x points, y points is equal to mesh grid x and y. We call it? Yeah, x1. Sorry, no, it's x1 and x2. I apologize. x2 and x1, x1, x2, semicolon, or else you're getting a lot of points here. And now I'm going to do a surface plot with all my x1 points, my x2 points, and my function I called func, where you send in x1 points and x2 points. Okay? All right. So I run a surface. Let me close all my plots so it shows up. There we go. Look at that. You've got here a bowl. Look at that beautiful bowl that pops up. Nice, nifty, cool, neato, awesome, great. Okay. Now, so clearly that's a convex function. Okay. It's all very concave up. There's a bowl, right? But let's start messing with the coefficients of that function. So here's func. Okay. And instead of making it x1 plus, and I'm hitting up, by the way, to to go back to previous commands, hitting up on the keyboard. Okay. All right. So instead of x1 squared plus x2 squared, I'm going to make it plus 0.5 times, make it 0.5 times x2 squared. Now I'm going to replot that surface plot with my new function. And there it is. It looks kind of similar. It's a little flatter on one side, right? Okay. Now let's actually change the function to make it maybe minus 0.5 times x2 squared here. Minus 0.5, just a little minus sign right there. Rerun it. I'm going to close my plots and rerun my surface plot. Look at that. Now we have things that are sort of they're convex on one side and non-convex, in fact, concave, going in other directions, right? And these interactions can become pretty crazy looking when you have many, many dimensions. We're just looking at 2 dimensions. This is called does this look like a saddle? It look like a saddle? We'll often call that a saddle point in the middle. It looks like a saddle, right? So how could we detect just from these coefficients? Again, it's not always as simple as whether or not there's a negative value in there, because here's what we'll do. Let's make this positive again, and then we'll add maybe x1 points times x2 points. Okay, it's now positive 0.5, and we have this x1 points, x2 points. That's my new function. I'm going to plot it again. Interesting. Still looks kind of convex to me. Let me do it again, except now it's 2 times x1 points, x2 points. Hey, look, all these coefficients are currently positive. Keep in mind. Close all. Plot again. Whoa. Look at this. Look at this. See that concavity? It's pointed down. All of my coefficients, here's a coefficient of 1, here's a coefficient of 0.5, here's a coefficient of 2. They're all positive, and yet it's still not convex. So how would we detect it? Well, what we can do is take the Hessian, right? So in fact, what I'm going to do is I'm going to create some symbols. Call them x1, x2. I'm going to define my function. F is equal to exactly what I had above, which is x squared plus 0.5 times x2 squared. Don't worry about I'm not doing dot multiplies for a reason here. This is all symbolic math. Plus 2 times x1 times x2. Okay? There's my symbolic function. I can take the Hessian h of that symbolic function f. And there's my Hessian. 2, 2, 2, 1. And what I can do is I can take the eigenvalues using the eig function of a matrix. Okay. So I take the eigenvalues h, and you can only take the eigenvalues of a square matrix if you've never seen it. And if it's a 2 by 2, there are 2 eigenvalues. If it's a 3 by 3, there are 3 eigenvalues. So let's take the eigenvalues of h. Okay. Those are my 2 eigenvalues. Those might be hard to read symbolically. So let's turn them into floating point numbers by changing it to a double precision. And voila, one of these is negative. So it's not convex because not all eigenvalues are greater than or equal to 0. I'm just typing that out. Okay? Any questions about the convexity, how you can check convexity of a cost function? It's not as simple as just looking at the Hessian and seeing if they're positive. Okay? Because if it's not convex, the solver will tell you. Okay. So let's get to some an actual example here. Let's code through an example with the last half hour we got. Okay, another example, a little more practical example. So here we go. We're going to use quadprog. So here's our next example. Use quadratic programming let's see. Should I do? I'm debating whether I should do the an abstract curve fitting problem or a more fun optimal control problem. I think we should do an optimal control problem. I think we can pull it off in the next 25 minutes, friends. I think we can. Okay. Use quadratic programming. Here we go. To find the feed forward controller f of t that minimizes effort for the following system. Where I'm going to draw a very simple system. Here's the ground. You can tell it's the ground by all the little diagonal dashes. I'm going to put a little mass, and I'm going to put a little force on this mass, okay? Okay? Very simple system. We're going to push, basically we're going to be pushing on a block, okay? So we want to find a force F of t right here such that we start here and we end over here. We'll call this position, we'll call it S of t. And we'll call this position, that's S equals 1. And this here is S equals 0. Okay, where it starts. Maybe I'll redraw that slightly. Okay, and we're going to minimize effort. We're going to say our cost f of w is equal to the integral of capital F of t squared dt from 0 to the final time. So basically, if you're applying force be it positive or be it negative, it's going to be squared, and therefore it's going to incur a positive cost, right? Which is bad. Okay? And we're going to say that we want to arrive here at rest at t equals 5 seconds. It's like, what? This is accelerated quickly. This complexity accelerated quickly. We're doing control with quadratic programs? How could this be? How could we pull this off? I'm glad you asked, friends. Glad you asked. Okay. So we have a system that we can for which we will need to know how it's going to get from point A to point B. We have 5 seconds to get there. We want to minimize the effort while we get there. Okay? And so that means we are going to need, if we have a dynamical system, we're going to need the equations of motion, or the dynamics. In the form of a differential equation. Well, if you sum all the force, we all know F equals ma, right? Sum of the force is equal to mass times acceleration. And in this case, our acceleration is s double dot of t. Let's assume that m equals 1. We're sliding without friction, so there's no friction forces. We'll say no friction, no friction. So the sum of all of our forces, our only force is going to be our external force, F of t. So that means it's going to be capital F of t is equal to m s double dot of t. So in effect, if we're solving for s of t, okay, if we're going to solve for s of t, if this is going to be integrated, we're going to be taking this and integrating it twice, right? So this actually has a name in the system. It's called the double integrator. All right. I'm throwing a lot of stuff at you, but not stuff you haven't seen before, right? You've seen dynamical systems. This is a really simple one, right? Okay. We're going to turn this into a quadratic program, this problem. Okay. You know how we're going to do it? We are going to take these dynamics and we're going to define our force over time in a way we can put it in a decision vector. Okay. Now, you've all experienced this in your homework where we defined some input force or some control input, in this case F of t, as a spline, right? As a spline, meaning it's a series of points that are connected by curves, okay? And we're actually going to define it in like this. We're going to say that F of t is going to have, over the course of 5 seconds here, we're going to define a point here, 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 here. Okay? Where our force is going to be applied like this. Okay? Where for the first second, it's going to be applied by some amount. What amount? I'm glad you asked. Well, we don't know. We don't know. Okay? Apologize for the color discoloration. I'm not sure why it's doing that all of a sudden, but you can, I wrote that as blue. Okay? So that means, and what we will in fact define is that they're going to be 1, 2, 3, 4, 5 different segments here. Okay, 1, 2, 3, 4, 5. And so what we're going to do is we're going to say that this time step here, this is our delta t, okay? And we're going to use Euler's method to integrate from one state to the next, okay? So we need to have our state space. These are just guesses. So I'm looking at those. So it's a great question, okay, Logan? Right now, the height of these are just guesses. But the optimization is going to decide what the actual heights are going to be. So our decision vector, W, we'll call this one force 1, force 2, force 3, force 4, force 5, right? So our decision vectors could be F1, F2, F3, F4, and F5. That's our decision vector. And I just drew it at these arbitrary heights so you get the impression that the optimization, it can mess around with these levels. Okay. That's our decision vector. Okay? What's our cost function? Our cost function is actually pretty simple too. Kind of, right? It's going to be the our cost function, lowercase f of w, it's going to be the integral from 0 to capital T of our force over time squared dt. Now that's approximately equal to, how would we compute that integral when we have like these little rectangles like this, right? We can use the rectangular rule and sum up the area under all those rectangles, keeping in mind we have to square the force. Well, that's easy. It's going to be F1 squared times delta t plus F2 squared times delta t plus ... all the way out to F3 squared delta t. Another way to write that is that, hey, it's just the sum from I to n, where you have n points, of Fi squared all times delta t. That's our cost function. Does anyone think that's a linear cost function? Does anyone think that's a quadratic cost function? Yeah, looks like a quadratic cost function to me. You have all of the decision variables, our forces we get to decide, squared, right? That's going to be a quadratic cost. So let's start with that, okay? Let's start with those. So if we want to define, so let's define that cost function, okay? Like that. That leaves our constraints. Now, does anyone want to tell me in their own words, for this problem, what are our constraints? Anyone have any ideas? If I go up to here and show you. What does this system have to do? What must be true in order for this to work? Well, I'll tell you. Yeah, time and position, correct. Right? So we got to arrive here at t equals 5 seconds, and we have to arrive exactly here at rest, at s equals 1, the position s equals 1, and also that s dot has to be 0. It has to be at rest, right? Has to come to rest. Now, if we, by default, make sure that it only ever simulates for 5 seconds, then we don't even need an equality constraint for it, okay? So our two equality constraints are going to be S1 is equal to 0 and S dot is equal to 0 at this final time, 5 seconds. So how do we get that? We get that with Euler's method. We use Euler's method to simulate. So we're going to say our final position and velocity, say at 5 seconds, equal 1 and 0 respectively, right? So how do we know what our final position and velocity are based on our decision variables? I mean, because clearly, whichever decisions we make in terms of the force are going to determine how far it goes, right? Right? That's not crazy. Okay? So what we're going to do is we're going to integrate, we're going to simulate our system using Euler's method. So if you have some s at time 0, which we know is equal to 0, it starts at the starting line. And S dot of 0 is equal to 0. It starts at rest. That means that S at 5 seconds, okay, is going to have to be equal to S at 4 seconds plus S dot at 4 seconds times delta t. Do you agree with me? Oh, so yeah. So do you agree with me there? Right? And S dot at 4 seconds is going to be equal to S dot at 3 seconds plus S double dot at 3 seconds times delta t. All right? And S dot at 5 seconds is going to be equal to S dot at 4 seconds plus S double dot of 4 at 4 seconds times delta t. I wrote them slightly out of order. Okay? And you can keep doing this, right, until you get back to S at 4 seconds is equal to S at 3 seconds plus S dot at 3 seconds times delta t, right? And if delta t is equal to 1, this makes our life really easy. Until you get all the way to the point where you have S dot 2 is equal to S dot 1. Sorry, S dot at time 1 is equal to S at time 0, S dot at time 0 plus S double dot at time 0 delta t, and S of 1 is equal to S of 0 plus S dot of 0 times delta t. I kind of went in reverse order from the end to the beginning. Okay, so this is at 5 seconds. 5 seconds. This is what we want to be true for our constraints, that this is going to have to be equal to 1, and this is going to have to be equal to 0. Okay? So what we can do is use this to build a constraint that, when we take that when solved, puts our system at that final position. Okay? Now, these S double dots, look at all these. S double dots, that just means we get those from our equations of motion, right? So we'd say S double dot times m is equal to f of t. And therefore S double dot is equal to f of t divided by m. And this should be S of t, I apologize. Okay. All right. So that means that at this point right here, this S double dot of 0, that's going to be the force we are applying, f of t, at time 0. Well, what force are we applying? Let's go all the way up to here. At time 0, we're going to be applying F1. So that right there is going to be F1 over m. Okay? So here's what we're going to do. We're going to go back into MATLAB. And we're going to use the symbolic toolbox to help us build a quadratic program that will solve this problem. Okay? All right. So, back to our code. So I'm going to save a new script. I'm going to call it double int qp. Double integrator qp.m. All right? By you and me, Christian Hubicki et al. Here in 2025, 02/13 of the Common Era. And we are going to use a QP to solve the minimum effort solution to a double integrator move. We're going to clear everything. We're going to clear the screen. We're going to clear all the variables. We're going to close all the plots. Okay? All right. Now we're going to define our parameters. We're going to say that m is equal to 1. We're going to say that our final time, so we're going to say our delta t, our dt, is equal to 1. And we're going to now define, so what else do we have? Any other parameters? Okay, we're going to put our final position, S final, is equal to 1. I'm going to put our ds final, which is our final velocity, is equal to 0. Okay, so final position. This is our time step. And we have our final velocity. Okay. Now we're going to define our decision variables as symbols. This will allow us to compute Hessians, etc., symbolically. Okay? So we're going to define, we have symbols, we're going to have F1, F2, F3, F4, and F5. Okay? We have our symbols. I'm going to put them all into one decision vector. W is equal to F1, F2, F3, F4, F5. And I want to put semicolons in between them. Keep in mind, if you want to try to do a transpose, remember to do a non-conjugate transpose by doing that, okay? So now we have a decision vector. I'm just going to run it to make sure I didn't make any errors. Hey, look, a decision vector there, okay? Now we need to do our cost function. Okay, and you'll notice that a lot of this is setup. You'll notice there's a lot of setup on my whiteboard, and then I finish it off by putting it into code, right? All right. So here we go. We have our cost function. Here we go. All right. It is all of our forces squared. We sum them up and multiply them by delta t. So we could write this all out as F1 squared. You know, I'll do it just for clarity, but you could do it much simpler with the sum command with W. But this way you can see what's happening. F1 squared plus F2 squared plus F3 squared plus F4 squared plus F5 squared. All times delta t, which is our time step. Make sure that all runs. Hey, there's our cost. Beautiful. Okay? All right, now for our constraints. And this is, by the way, our minimum. This is minimum energy, minimum effort, Okay, we want our final. So we want to let's first compute our final position and velocity. Okay, so let's go down in our code here. Let's scroll down to the bottom. All right. So let's look at the bottom here. It says that, let's just say that S1 dot, or call it DS1, is equal to DS0 plus so DDS0, which is DDS0 times delta t. Okay? This requires that we define where our initial velocity is. Well, we know what that is. We know that we said that we're going to start at rest. ds0 is equal to 0. And by the way, yes, there are far easier ways to write this out, but I'm trying to make it as verbose as possible so it's as clear as possible to follow. So this is our initial velocity. And while we're at it, let's give our initial position. S0. That's our initial position. S0. So here are our Euler steps to integrate our dynamics. I'm going to say ds1 is equal to ds0 plus dds0 dt. And it's a similar thing for, let's say, S1, which is equal to S0 plus ds0 times dt. Do you agree with me on that? These are just Euler steps to integrate our dynamics. This is our first step. Okay? We'll call it step 1. The problem is we don't know what DDS0 is. Oh, wait, what's it equal to? It's this F1 over M. So that means DDS0 is equal to F1 divided by M. Done. That's step 1. Let's copy that for our remaining steps. Okay? Copy, 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 copy. 5 steps. We're going to do step 2, step 3, step 4, step 5. Okay, I'm going to get rid of this so we can expand the screen so you can see it a little better. We're almost, believe it or not, we're almost done. Okay? So step 1 goes from 0 to 1. Step 2, so you got to integrate, update all these right here. So it's going to be ds1, then s2, s1, ds1, s2, ds1, ds1. Then, and yes, there are easier ways to do this, but I want it to be as verbose as possible. So S3 is equal to S2 plus ds2 times delta t. ds3 is equal to ds2 plus dds2 times delta 3. Finally, this is ds3, 4. This is 3. Just increment each of these. That's a 4. Increment each of these things by 1. Okay? S4, S3, DDS3, and DDS4. S5 is going to be S5 plus S4 plus S4, DDS5, DDS4, DDS4. Now, you do not want to do that way for homework, because what could have easily happened, right? I could have easily missed one of these substitutions. I'll just check 1 0 0 1 1 2 2 3 3 4 4 5 1 0 0 1 0 0 2 1 1 2 1 1 3 2 2 3 2 2 4 3 3 4 3 3 5 4 4 5 4 4. Great. All right. So if I run that, it's going to probably push a bunch of stuff out to the screen. Okay, but you can see, hey, look, there's an expression for what the position is at S5, and the velocity is at S5. So what do we want them to equal? We want them to equal 0, and those are our 2 constraints. Okay. So thankfully, our GEQ is going to be these 2 expressions have to be equal 0, right? So we'll say S5 and ds5. And that's our equality constraint, right? And we're motoring through it again. If you have to go, I apologize. I'll keep recording. This shouldn't be more than a few more minutes to finish this up, because we've set everything up. Now, MATLAB computes our Hessian, gradients, and Jacobians. Okay? So let's compute our Hessian of our cost. So let's call it H is equal to our Hessian Yeah, Logan, if you want to set this up as a loop, you can choose either way to set up the iter from 0 to 4 or 0 to 5. It depends upon which iter you put into your indexes, right? Okay. If you want to say iter plus 1 or iter, they're both ways can work. Okay. The Hessian of our cost, f, or do we call it cost or we call it f here? Call it cost. Call it cost. Hessian of our cost function with respect to our decision variables, w. Okay, let's run that real quick to show you. Oh, look at that Hessian. Look at that. Boom. And we'll save ourselves some trouble by making it into a double. Save ourselves some trouble by turning it into a double. So it's a floating point number. Now let's do our gradient. We'll call it C. Now our gradient is going to be our gradient of our cost with respect to W. Voila. Oh, wait. Isn't it interesting though? We still have these decision variables in there. Okay, we have to substitute in zeros for our decision variable. Okay, so C is equal to the substitution of C. Where there were once decision variables, we want zeros of the same size. Okay, substitute in zeros. So we run that. Okay, but we want to save ourselves some trouble by making it a double. Okay. In fact, I'll put it on the next line so you can follow it. So C is equal to double. Because right now, currently, C is the symbolic expression. Here, it'll make it a double expression. There we go. All right, we have H, we have C. Now, we have no inequality constraints. So A is equal to open, close. And B is equal to open, close. We have no inequality constraints. But we do have equality constraints. And the way we solved those, it was with the Jacobian. We said that AEQ is equal to the Jacobian of GEQ, which was that function we just defined, with respect to our decision variables, W. Oh, look. AEQ, DEQ, sorry, look, there's our AEQ. Nifty, right? Save ourselves some trouble, turn it into a double. So that way, these are floating point numbers before they were symbolic numbers, okay? And BEQ, you'll recall that what we want to do is take that expression of our GEQ, okay, and substitute in zeros for where there were decision variables. So we substitute in GEQ, where there were once decision variables, we want zeros of the same size of our decision variables. So make sure this is a 2x1 of zeros. And we want to put it on the other side of the equation, just like last time, okay, with our linear constraints. Look, and it's 0, 0. That's actually the right answer, except we want to save ourselves some trouble by making it into a double. So now this is a type double, so floating point number. Yep, let's pull up the GEQ. 1 second, friends. There's GEQ right there. Okay, so we are really close. We have AEQ, BEQ. So let's solve W star. Let's solve our quadratic program. We have everything. Hessian, H. Our gradient, C. Our A matrix, which is open, close bracket. Our B vector, which is open, close bracket. Our AEQ and our BEQ, they're all defined. Okay? I'm going to run it. So let's solve RQP. Run it. And it ran. Oh. Wait. It didn't go anywhere. Why is that? Oh, I made one mistake, friends. Here I said that I want my final position to be 0. That's not true. We want it to be at our final position, which I believe we called S final, right? So that means that we don't want S5 to be 0. We want S5 minus our final position to be 0. So that means perfect. And our ds final is the same thing. So back in your GEQ, run that. Oh, gorgeous. We fixed it. There's our answer. For the first second, you apply 0.2 newtons. For your second second, you apply 0.1 newtons. For your third second, you apply 0 newtons. For your fourth second, minus 0.1, 0.2. And this thing, if you simulated it with the Euler steps, it would come to rest. Okay? Let's write this out. Say, we want the final position to be S final. Therefore, S5 minus S final equals 0. That's why GEQ has to equal what? 0. Since GEQ of W must equal 0, our two constraints that must equal 0 are S at 5 minus S final and S dot of 5 minus S dot final must equal 0. That's it. We solved it. We've done everything today. We did a really simple quadratic program, and we just did an optimal control quadratic program where we came up with a feed-forward force over time. I'll show you what it looks like. If we were to plot, close all, let's plot 0 through 4 as our time as our time points, and all of our force points W star. And let's make them just big X's. Let's change the marker size to something big like 10. I think that'll work. Okay. It has a big X up there, X right there. Boom, look at this. This is actually the right answer. So basically, it's saying push big at the beginning and then ease off and then start putting on the brakes and pulling back. And that's how this system is optimally controlled for that cost function. So I'm happy to stick around for a few more minutes and answer some questions and show some code if anyone needs to see any element of this. But look, we started from scratch and did an optimal controller. How cool was that? All right, friends. Thank you so much. Really appreciate it. Have a great weekend.